Well then, lesson 3. Lesson 3 hits us with some pretty serious stuff, almost right off the bat. Natural logarithms are where we're going to park ourselves for the next little while. If logarithms scared you the last time you studied them, they're a little bit different here, but not much. If you remember things about logarithms from before, that's going to be super helpful now. So let's begin with a definition. By definition. Wow, I need something calibrated. That is so ugly. I'm sorry. By definition. When we talk about the natural log of x, and this is something that you probably studied in Algebra 2, and so you have a completely different frame of reference for what the natural log of x is. By definition, in our course, the natural log of x is an integral. It is the integral from 1 to x of 1 over t dt if x is greater than 0. There is no way your Algebra 2 teacher gave you this definition because you would have cried, period, amen. But we can talk about this because you are familiar with this notation from Calculus 1. So here is 1 over t. Here's 1 over t. Here's 1. That's the 0.11. So 1 over t is this red function. The natural log function will be the blue function. So let's remember some things from Calculus 1. We're integrating the red function from 1 to x, and that will give us the natural log of x. So if we want the natural log of 1, let's say, that's the integral from 1 to 1, and that integral is 0. So the natural log of 1 is 0. And then what happens as we move toward the positive end of the x-axis? As x gets bigger than 1, we're accumulating positive area under the red graph. So as we go, the log graph increases, which makes sense. We're getting more and more positive area under the red function, but that area is decreasing as we go. How that area is increasing is decreasing because this red function is decreasing. So what does that mean for the log function? That means that the log function is increasing, but it's concave down. We're increasing because the area is increasing, but we're increasing in a decreasing way because the red function is decreasing. As we move toward the x-axis, this area is increasing, but we're reading from right to left, so the integral values are negative. And this is the way you probably thought to graph the natural log function. A couple of notes here. One is that t is a dummy variable. It can be any variable in the world except for x. Why? Because x is this thing. That's what changes when this changes. So we don't use that same variable here because this is some function that's graphed on the page, and this is the argument of the natural log function. The other question deals with this. Why do we restrict? So why do we restrict x to be positive? Well, if we let x be negative, then there's this whole matter of this red function never touching the y-axis. So we restrict x to be positive so we don't have to deal with an integral that crosses over a point of discontinuity. Also, the other thing for us to talk about on this page is what e is. E is the number whose natural log is 1. So here's y equals 1. This is the place where y equals 1. This is e. E is the number whose natural log is 1, and it is approximately 2.718828459045 approximately. I know more digits of E than of pi, and we'll get into why when we gather in class. So this is the natural log function. You are familiar with it from your time in high school, but we define it in a rigorous way here in terms of a definite integral. So the first important takeaway is how to find the derivative of the natural log function. What is the derivative of the natural log function? Well, we can probably prove this without too much trouble. The derivative of the natural log function is the derivative of an integral from 1 to x of 1 over t dt. So now I have to remember the fundamental theorem of calculus part 1. How do I take the derivative of an integral from a numbery thing to a lettery thing? Well, it's this with that substituted. And this is by the fundamental theorem of calculus part 1. So the theorem says that the derivative of the natural log function is 1 over x, which enables us to find the derivatives. Let's see. Um, let's find the derivative of the natural log of 5x. Let's find the derivative of the natural log of sine x. And let's find the derivative of the natural log of the natural log of x. In no case is this terribly difficult. The derivative of the natural log of something is 1 over something. Chain rule requires that we multiply by the derivative of that argument. You remember the chain rule. And so, well, it turns out that the derivative of the natural log of 5x is the same as the derivative of the natural log of x. Well, that's interesting. G prime of x, well, the derivative of the natural log of something is 1 over that something times the derivative of that argument. And this is sometimes written as the cotangent of x. And then h prime of x, the derivative of the natural log of something is 1 over that something times the derivative of that argument. And that is sometimes written in this way. So that's the basic idea. The derivative of the natural log function is 1 over x, and we use that and the chain rule to find derivatives. Let's go this way. There are properties of logarithms that you remember from high school. Those properties also extend to the natural log function. We can prove all of them off of the definition of logs that we've just talked about. I'm going to say that b is a positive number, and I'm going to say that x is a positive number. Then there are some things you should know. The log of a product is the sum of the logs. The log of a quotient. That is terrible. I am going to try to erase this. I'm so sorry. It is the difference of the logs. The log of x to a power. Power comes down in front. And the rule you're still used to, if you have a log in some base that isn't e, that's just the natural log of x over the natural log of that base. I'll prove one of them here just for kicks and giggles. I'll prove this one. So we're looking to show that this is true. I'm going to do it through a back door. Let's take the derivative of the natural log of x to the p. The derivative of the natural log of x to the p is 1 over x to the p times the derivative of x to the p, right? It's the derivative of x to the p. That's px to the p minus 1. Well, what's that? A bunch of these cancel out with a bunch of those, and you get 1 over x times p. Well, p is just a number. 1 over x happens to be the derivative of natural log x. Well, so what? Well, that p can come and play inside. So now what do we know? We know that the derivative of this thing is the same as the derivative of this thing, which means that these two things are either equal or they differ by a constant, and we can prove that that constant is in fact 0 just by substituting 1 for x. That will do the trick. If we substitute 1 for x, we see that both sides are 0, and so the constant is 0. So all of these properties of logs that are familiar to you from high school can be proven using the definition of log that we just laid out. Time for me to lay out our first OYO. These are questions for you to do on your own. So they're things that we can talk about when we gather, but for now, they're things for you to do on your own. Let's make sure that you know how to take the derivative of x squared ln x, and that you know how to take the derivative of the natural log of radical 5x plus 1. And then let's make sure that you know how to find the equation of the tangent to y equals natural log 2x minus 1 at x equals 1. If you're looking for extra questions to play around with because you're like, well, I want to make sure I have this down, in Volume 1, Section 3.9, you might want to take a look at questions 340, 341, and 356. And we can talk about any of these when we gather in class. Thanks for sticking with me for 13 minutes. We'll see you then.